I'm going to talk about human-compatible driving partners through data-regularized self-play RL. And so the motivation for this work is that, for the foreseeable future, autonomous vehicles must be compatible with other humans on the road to be deployed safely. And here, really a central challenge is to coordinate with humans. So what are the missing ingredients? Well, what we currently have is we have a lot of different driving simulators that all have different advantages, but simulators are great because they offer a safe and cost-effective way to improve autonomous vehicles, or to improve and evaluate autonomous vehicles. And what we also have is we have a large quantities of traffic data available. Maybe some of you are familiar with the Waymo Open Motion dataset, for example. And these data sets have, if now I've worked so far with the Waymo Open Motion dataset, and this dataset consists of 100,000 traffic scenarios, and every traffic scenario has a number of agents in there, a number of vehicles that drive from A to B. So you have a number of road maps, but you also have human driving trajectories. So, but what we don't have at the moment is realistic human-like driving agents. So, yeah, this is what we're trying to work on. So yeah, given the data sets we have and the simulators available, so how do people typically populate their simulators with driving agents, right? Let's say you want other driving agents in your simulator. How can you approach that? Well, there are a couple of different ways. One approach is to use rule and heuristic-based methods. So maybe some of you are familiar with car following models or variants. And here the idea is that you have a small set of parameters that determines the behavior of your agent. And one advantage of this is that it's quite reliable. It's very interpretable, and these models respond. But one con is that they don't really capture nuances of human behavior that I think we need, and they're easily exploited. Then another strategy that you can apply is to just replay the existing human logs, assuming that you have these available. And so here you would just, tag one vehicle in a scenario and control that with your policy, and then have them interact with the static human logs. And these are basically humans, like your proxies for human behavior, but they don't respond, so they're not reactive. And if you have a very popular approach for creating policies from large amounts of data is imitation learning. But one disadvantage of this is that these type of approaches, these pure imitation learning approaches, have empirically high crash rates in closed loop settings. And another thing, that image is a bit vague. I don't know what happened there. But another thing you can do is you can use reinforcement learning and train agents in closed loop settings to achieve a particular goal or a particular set of goals. And this is, advantage here are that these agents are reactive and reliable, but one problem here is that it's very hard to constitute to design a reward function that constitutes human-like driving. Like, this is very hard. And so just to give you an example here, what happens if you just do RL, and use self-play, so multi-agent RL? Well, so here you can see in the green agent that is just told to drive to a goal and not collide. And you can see that this agent, this green agent here, by the way, and the other is also green, but we're looking at this agent. This is in some sense safe, but this is not like what we want at all. This is not, a human would never really do this. So it's just quite hard to specify a reward function that gives us the type of behavior that we want. So what we do in this paper is we combine multi-agent reinforcement learning with imitation learning to obtain driving agents that are both effective and also human-like. Oh, by the way, since we are not with that many people, feel free to interrupt me if you have any questions. Okay, so how does this work? Well, we have a two-step approach. Basically, first, what we do is we use behavioral cloning to obtain a human reference policy from only 30 minutes of driving data. And one sort of finding, or one thing that we learned through this project, is you really don't need that much human data to get this to work. So yeah, we just do behavioral cloning where you minimize the negative log likelihood, and you learn a distribution over actions conditioned on a certain observation. So once you have that policy, you just take that fixed policy and then you use it to do what we call guided self-play. And guided self-play is essentially PPO, but with additional regularization. So you basically use PPO and you add a regularization term to this behavioral reference policy. So let me just break it down. This is your new human regularized loss function, where this is the standard PPO loss. So this is a combination of the entropy term, the advantage, and the value function. And then what you do here is you have the KL divergence between the behavioral reference policy tau and your the policy that you're learning. Pi, this should actually have a subscript pi subscript t, so it changes, right? And this parameter lambda here controls the importance of both objectives. So if you set lambda to 0, then you basically have standard PPO. And if you set lambda to a larger, so to a positive value, then it somehow balances these two. So lambda is between 0 and 1. Yeah. So where do we do, how do we, implement our experiments? Well, we do everything in this paper, we did everything in Nocturne. And Nocturne is a multi-agent driving simulator based on it works with a Waymo open motion data set. So the simulator is built on top of this data set. And on the left-hand side here, you can see an example scenario. And this is a bird's eye view. So you can see all these boxes, there are vehicles, and they go to their respective destinations. And on the right-hand side here, you can see what this blue vehicle is seeing. So it's partially, the setting is partially observable. And I thought this would be a nice time to briefly talk about our new simulator, GPU Drive. So maybe for some of you that are doing RL, maybe this sounds familiar to you. Yeah, some RL experiments can take a long time. So the experiments that I'm presenting to you in this presentation took about, the results took about 5 days to generate in Nocturne. And so to basically improve or allow researchers to iterate more quickly on multi-agent research, we built GPU Drive, and this is a collaboration with a number of really great people: Sam, Araf, Brennan, and Eugene. And what we basically built, I'm not going to go into much detail, but we built a GPU accelerated simulator that's built on that uses the Madrona framework. And our simulator can achieve over 2 million frames per second. Yeah. So in this figure, the blue line is Nocturne. So this is what I used in this paper. This is the agent FPS. So this is the number of agent steps per second of Nocturne. And then in pink, you can see the agent steps per second of GPU Drive. So you can see there it's like 2 to 3 or 3 to 4, even if you compare to this one, orders of magnitudes better. And just to show you what that really means for if you're doing research, well, runs that take 5 days in Nocturne take about 3 hours in GPU drive. Yeah, and there are additional speed ups that can be done here if you are implementing your algorithm. But yeah, if you have questions about that, you can. I'm happy to talk about that offline. So yeah, here just to show you the difference, I plot the global step of the I plot the training performance as a function of the global step. And pink is GPU drive, blue is Nocturne, and you can see it's sort of the same. And on the right side here, you can see the performance as a function of raw clock time, and you can see that this just saves you a lot of time. Lastly, we also support different observation types in GPU drive. So we have one that's called radial filter. This is yeah, basically where you take the n closest steps, n closest points around the vehicle, and on the right hand side you can see LiDAR. So you can also, do experiments with LiDAR. Yeah, so the repo is here and the link is here if you're interested. Any questions about this? Otherwise, I will go back to the normal presentation.
No, thank you. It sounds really great. A lot of people in the group. Oh, Caleb, perfect. Speaking of the devil, Caleb, go ahead.
Cool. Yeah, it looks very cool and very interesting. I'm just curious for people who are maybe more in like pure RL, what would be the like incentive to try an environment like this compared to the current baselines? Like how do you think? Like, is it just because it's more realistic, or is there more complicated dynamics?
You mean compared to standards, like what kind of benchmark did you have in mind, or what is the environment that you currently work in?
Like a standard, let's say, physics-based multi-agent environment, like maybe VMAS or SMAC. Yeah, I'm just trying to understand, if you're not like focused in the driving domain, what would be the incentive to test in this environment? Like, what kind of behaviors do you think would be hard to, I guess, even evaluate in other environments that would be possible to evaluate in this environment?
Yeah, good. That's a really good question. So I think what this environment is very useful for is to test coordination. So like some of our all of the scenes are contain a lot of agents. So scenarios contain between let's say 1 and 50 agents that you can control. So yeah, it's just quite a complex coordination problem, and that's one thing. And another thing is, yeah, it's based on real data, which can be nice. And yeah, I think that it's so I'm not like I'm not an expert in SMAC, for example, or these kind of environments, but another nice aspect is that you can choose any vehicle in the scenario to control. So you can also easily use different policies to control different vehicles in the scene, and then yeah, test coordination with that. So I think, yeah, if you're interested in coordination, or it's not really like a cooperative. This is like more as a general sum game, although you can also change the rewards. But if you're interested in coordination, then I think this offers a nice alternative. Plus, you have a lot of human data available, and I think that's a big advantage as well.
Okay, cool. Yeah, that sounds great. I think there's very little human data in other environments, and I think it's nice that you can choose which vehicle to control. Okay, cool. Looks very nice. Thanks.
Thanks for the question. Okay, then I will continue.
Sorry, yeah, there's a question from,
Sorry, can you go back to your last slide? Previous slide.
This one or this one? Yeah.
Yeah, so here, LiDAR, have you also integrated a sensor model in the simulator?
Can you say that again?
Have you also integrated the sensor model LiDAR into the simulator? So what do you mean LiDAR here?
Yeah, it's just so I'm not really, to be honest, familiar with the specifics, but yeah, it's a LiDAR within the simulator.
So you can simulate
but
the
let
point
me,
cloud.
yes.
Okay,
I
you
think
try
it's
to simulate the
something
point
like that.
cloud in the simulator, right?
I have to check this, but I think this is how it's implemented. But let me actually check this offline, and then I can get back to you if you're really interested in using it.
That sounds interesting because if you integrate such a kind of sensor model in your simulator, you can also test your perception. Not only you can also test or train your perception, not only your motion planning, right?
Yeah, that sounds interesting. Yeah, I also know that so the Waymo Open Motion, the Waymo Open Data set also has LiDAR, but this is not what we're using. So it's generated in the simulator. Yeah.
Okay. Does your simulator currently only support the Waymo dataset?
At the moment, yes.
Okay.
But we are also interested in extending to different data sets. And there are some efforts, like not yet in our team, but I know that there are some people working on aligning data sets from like NewPlan and the Waymo Open data set. So I think I would really like to, at some point support multiple data sets. I think that would be nice.
Okay. So you're currently very actively developing this simulator to make it support multiple data sets.
Well, so currently we're not actively working on it, but we are. It is on the list. Like, yeah.
Okay, thanks. Great.
Yeah. Oh, sorry. Okay, so let me continue to or go back to the, the human compatible driving agent. Oh, sorry, no, another question.
Sorry to interrupt. I think that Tish is also at a question. Sorry.
Yeah.
Okay.
Sorry, my question is quite simple. So in this one, in this slide that you have here, there is the spy control and human replay. What's the difference between the two here?
Oh yeah, good question. So here, I just wanted to show the fact that you can easily control vehicles with different policies. So what I mean with the pink vehicles are controlled by a policy that is trained through self-play, and the blue vehicles are just replaying the human log. So actually, I called this log replay in this presentation, but they are called human replay, which is not consistent, but it means the same thing.
Okay. All right. Thanks.
Yeah.
I think we don't have any more questions. Thanks for
okay. Okay. So method. So yeah. So we only reward agents for getting to their goal position, which is just the end of the expert trajectory. So we just give the agents +1 if they achieve the goal, and if they collide with another agent or if they drive off the road, then they are removed from the scene. So they're incentivized to, not collide and not try, like, stay on the road. And yeah, so we basically don't do any reward shaping really. Then we have two types of metrics to evaluate the agents. So we have effectiveness metrics, and we have realism metrics. So effectiveness here is just the off-road rate, goal rate, and the collision rate. And realism metrics, they measure how similar the generated trajectories are to the ground truth human trajectories. So you have the average displacement error, which is basically just looking at every time step, takes a difference between where the human was, and then where the policy is, and then it just averages that. And we you can also look at the action differences. So this is just at every time step, which action did my policy take and which action did the human take. And we have 4 of these realism metrics, but I'm only gonna show you the ADE here. But in the paper we have yeah, there's more details. So results. Ooh, 1 result. So the first result that I will tell you about is basically about, is there a trade-off? So is there a trade-off between human likeness and or realism and effectiveness? And basically the answer is no. So what we find is that human regularized PPO agents are significantly more human-like according to our realism metrics, and also match PPO's performance. So on the x-axis, I show you the average displacement error, and on the y-axis, I show you the goal rate, off-road, and collision rates. And what you can see, so here we have PPO in purple, where you can see it's very effective, high goal rate, but it's not human-like at all. And here we have behavioral cloning with actually our behavioral clone policy is quite bad, as you can see, but yeah, so it has a goal rate of 50%, but it's very human-like, all to the left side. And if you use a lambda coefficient of 0.6 or 0.2, if you somehow balance these 2 objectives, you can get policies that are both human-like and also effective. And you can see this in all the figures. Then, another way you can measure human likeness is to see how compatible the agents are with the static human logs. So the idea being that if my policy was perfectly human-like or perfectly like the other agents, like the human trajectories in the data, then it should not collide with these other agents. So this is what we're trying to measure, or what we measure now. And in these figures, I show you with the same colors, behavioral cloning performance, PPO performance in purple, and then human regularized performance, PPO performance in orange. And I have 2 evaluation modes here. We have self-play. So when I say self-play, I mean that we control all the vehicles in a scenario with the same policy. And log replay is when I tag a random vehicle in the scene that to control, and then the other agents in the scene are all static log replays. So these are the static human trajectories. And the interesting part of this figure is when you shift from self-play to log replay, the PPO performance test is a lot worse. So you can see this is about 5% collision rate, and this jumps to 25%. So clearly, these agents are not compatible with the human driving logs at all. But when you go from self-play to log replay for human regularized PPO, it only increases by about 5%. So we see that the overall, the human regularized PPO decrease the self-play log replay gap by about 10 to 14, 15%. This figure doesn't. This figure is the aggregate performance across 200 scenarios. It doesn't tell you the whole story, because actually, what we saw in that we saw that more than 70% of the vehicles in the Waymo open data set can just drive straight to their goal without interacting with other vehicles, and yeah, they can just reach their goals, so they don't really have to interact. So what we did is to more carefully evaluate, vehicles. We introduce a metric, which is the intersecting paths, to measure the interactivity in a scene. So here you can see on the left side, you can see a vehicle. This is a trajectory that drives to its goal, and this is like 0 intersecting paths because it doesn't have to coordinate with any vehicle. And on the right side, this is a highly interactive scene where we're controlling this vehicle, and then like look at how many vehicles there are that it should coordinate with. So this one definitely, maybe, I mean, this also depends on time, right? So it's hard to say from a static picture, but I know that this scene had 3 intersecting paths. So yeah, basically this captures to some extent the interactivity in a scene. And what's interesting is if you then plot the collision rate as a function of the number of intersecting paths in a scene, so our proxy for interactivity, you can see that PPO almost kind of linearly increases as a function of the number of intersecting paths. But human regularized PPO kind of stays constant, and this collision rate is still way too high, so there's room for improvement. But yeah, you can see that on the more interactive scenes here, human regularized PPO outperforms PPO by about 20 to 40%. So I thought that was an interesting finding. And let me just show you 2 example behaviors, and there are a lot more videos on the project page. So if you want to see more, and also failure cases. So if you're interested in that, go take a look there. But here on the left-hand side, you can see that that the PPO agent just like drives. It's not patient. It doesn't wait for this vehicle. And on the right-hand side, the human regularized PPO agent waits for a second, and then it approaches the goal. And if you remember the scene that I showed you in the beginning, where the agent just kind of I don't know how to call this, but it drives like this. And if you look at the same scene, but then control this agent with the human regularized policy, then it's just kind of patiently staying behind these 2 vehicles, and then it approaches the goal. So it's behaves more like we would want a human-like driving agent to behave.
Sorry to interrupt. I think we have Ben has a question.
Yes.
Ben?
Hey, can you hear me?
Yes, I can hear you.
Okay, brilliant. Okay. Well, thanks for the talk, I guess. Before I ask the question, I really liked your drawings and whatnot, because I think they give quite an amount of intuition as well as looking nice. My question is mainly about your reward design. So like you've already said that reward design is hard for these tasks, and it seems like you've gone for the simplest possible design, but instead you've like used more of a optimization based approach with your like action differences idea. So do you think that there's any future scope towards like improving the way that you're designing your rewards, or should we be focusing more in future with like kind of like these optimization tricks, or like going down the route of just trying to make the action probability distributions like similar to like how the human one looks, if that made sense?
Yeah. Okay. So it's a really good question. I have 2 things to say about this. So first of all, I think, so I think in terms of how we can improve the policies, my current intuition is that you want to use the data to create to learn the human-like behavior, because that's really hard to specify. Like it's very hard to sort of start from something, but once you have a policy that's sort of human-like, it's very easy to find, or we can use the rewards to fine-tune it to behaviors that we want to see. So for example, maybe if we want, and I have a slide about this in the future work one, but maybe we want a policy that's a bit more aggressive, or maybe we want a human-like policy that drives like a tipsy driver or something, like because we want our AV to be able to respond to those kind of agents. Like it's I think you can use the reinforcement learning part to fine-tune these human-like agents, but using the data or using an imitation learning policy is a really good starting point. So that was my first point. And then the second thing I wanted to say about the optimization part is that, what else am I saying? Oh yeah, so currently, and I'm not sure if your question is about this, but currently we're weighting every single prediction from the imitation learning policy in the same way. And I think it would be really cool to do this as a function of uncertainty. So if you think about it, like the imitation learning policy, probably if you are in the middle of the road, your imitation learning policy has seen this somehow. But let's say you, like, because you're doing RL, maybe sometimes you go to the edge of the road and you're still using your imitation learning policy to make predictions, then you probably don't want to weigh these predictions from the imitation learning policies here that heavily, because it has never been there, so it's probably going to be garbage, the predictions. So I think there's also room for improvement in terms of how you combine data-driven and RL imitation learning and RL approaches in the optimization step.
Yeah, great. That's pretty much exactly what I asked. I feel like I might have jumped the gun a little bit, seeing as it's in your future work section. So sorry about that. But
no, it's fine. No, it's fine. We can talk more about it if there's more time. But let me just get to the conclusion, and then we have time for more questions. So we introduced human regularized PPO, a multi-agent approach that uses human-like and effective agents. And I've shown you that the human regularized PPO self-play agents, they outperform PPO and behavior cloning agents across all different evaluation modes, and are also more human compatible with proxies for human drivers in interactive scenarios. So yeah, future work. So I think, yeah, there are a couple of really exciting future research directions, some of which I'm trying to work on all of these. But yes, so one is control and fine tuning. So first of all, the policies that I showed you here, they still have a 10% collision rate, and well, you ideally want to get to like 0% collision rate, or you want to make them like as controllable as possible. So that's why I have this thing right here. I think this would sort of be the dream, where you have a number of behavior axes that you kind of care about, and you would be able to like change these, and then as a result, your driving policy will change in terms of behavior, and in that way you would be able to test your AV with all of these, the whole wide range of human-like policies. So yeah, that's what I mean with fine tuning. So have realistic human-like driving models that also meet specific criteria. Then I think there's there's room for improvement in terms of evaluation. So how do we really evaluate behavior models? Like, how do we know that a model is human-like enough? I showed you some metrics that I used, like the average displacement error, but this is not a perfect metric, because like there might be a trajectory that's perfectly human-like, but it's just not the ground truth. So I think there's room for improvement there. And a really good, I think, initiative on this end is the Waymo Open Simulation Challenge, WOSAC, where they have a range of metrics. But yeah, I think we should work on interpretable and useful metrics for evaluating human-like behavior. And then a third point for future work is adaptation. And here the idea is that say that we have trained a policy in San Francisco, and now we want to adapt it to New York. How can you do that? So how can we design policies that can more quickly adapt to new situations and use memory to do that? Yeah. So thank you very much, and I would love to discuss anything about this work or other things.
Thank you so much. I think it was a great presentation. You were very clear. The problem was very interesting. So good job. Okay, I'll stop the recording now so we can have a conversation without fear of arriving on YouTube. Okay, perfect.